Hello, welcome to my talk on our multi-party computation protocol, Fantastic Four. This is joint work with Dalskov and Marcel Keller. The setting that we consider here is outsourced secure computation, where, for example, some clients want to compute a function on private data, in this case on banks, on credit card records, and they delegate this data to four parties who execute a multi-party computation protocol that produces the desired result. In this case, a machine learning model that helps predicting whether or not new credit card applications should be accepted. Privacy should be maintained. Privacy of the secret data should be maintained even if one party is actively corrupt. So this party can misbehave arbitrarily and privacy should still be maintained. Our contributions in this direction is a new four-party protocol that is suitable for computations over the integers modulo 2 to the k, tolerates one active corruption, and provides guaranteed output delivery. In particular, it provides the guarantee that the output is always produced, no matter how the adversary cheats. It has a very good communication complexity of 6 ring elements per multiplication, which is comparable to state-of-the-art protocols. And it does, unlike those protocols, it does not require function-dependent preprocessing, and it does not rely on expensive checks based on interpolation. I'm going to discuss this in more detail later on. As a bonus, we also introduce a three-party protocol. I encourage you to read the paper to learn more about how this protocol works. Now, our protocol satisfies the notion of a guaranteed output delivery in the traditional sense, but this traditional sense basically means that an honest party is trusted with the computation. Now, this is not very realistic, and this was already identified in the work of MPC with friends and foes, as it's called, from Crypto 2020, because none of the parties was trusted initially to carry out the computation in the clear. So suddenly you trust one of these parties because you identify it to be honest. Identifying it to be honest means actually it means that it is not corrupt. So it is not very intuitive and it's not very concretely practical. So as an alternative to this traditional model of guaranteed output delivery, we propose the following approach. So the four parties will execute the multi-party computation protocol as usual, and our protocol will guarantee that a semi-corrupt pair is identified. A semi-corrupt pair is simply a pair of parties where one of them is corrupt. If you want to go for the traditional GOD guarantees, then you can just use one of the two remaining parties to finish the computation in the clear. But instead, we follow this approach. The parties will kick out one of these two parties. Let's say they kick out P1, and the remaining three parties will execute an actively secure protocol with three parties with abort. If this protocol succeeds, then the output is produced and the computation is finished. But if this protocol results in abort, then the parties know that they kicked out the wrong party, so to speak. They kicked out an honest party. So the other party that was not kicked out, which is P4, is now kicked out at this point. And then the two remaining parties, P2 and P3, can finish the computation using a passively secure two-party protocol. Using this template, we can see that the secret inputs are never given to one single party in the clear, which provides stronger guarantees than the one in the traditional guaranteed output delivery model. Now, I want to stress that this model was considered in the Friends and Foes paper that I cited before, but our model here, our protocol, is not fully compliant with their approach because some technicalities that can appear. So we leave it as an open problem to completely formalize our model and make it compliant with the Friends and Foes approach. In terms of applications, we apply our protocol to several tasks, in particular multi-class deep learning and binary label logistic regression. This requires the introduction of different primitives that we do in our paper. I encourage you to read it for clarifying how these protocols work. And I don't want to get into the details of the concrete results that we get. I encourage you again to read the paper to see the concrete experimental setup, the different experiments that we run, and so on. But in particular, I want to look at the the highlighted section here, the highlighted numbers. We see that a protocol with semi-honest security and three parties that we use for reference only takes 0.4 seconds to train one dense layer for certain machine learning tasks involving digit recognition. Now, our protocol with malicious security and 4 parties takes only 0.6 seconds. That's less than half with respect to the 3-party protocol. So we see that the overhead from going to semi-honest to malicious is very low if you're willing to accept an extra 4th party. We also see that our protocol fares very well with respect to other works such as Swift, where these numbers that we can see here are obtained by extrapolating the results reported in their paper. And finally, we also report other metrics such as accuracy, which has not been done in previous works in this direction. Now, I mentioned that we don't rely on an interpolation-based check that is very expensive. Let me elaborate a little bit about how this check works. This is a check that was introduced in the work of Bonnet et al. At Crypto 19, and it was used in several other papers, such as the one from Boyle et al. At CCS 19, and also the protocol called Blaze and Swift. This is a check based on interpolation of polynomials that helps the parties check that several multiplications are done correctly. Now, if you want to interpolate over a field, we all know that this is completely possible, but if you want to interpolate over a ring, like the ones we considered in all these works, then you need to take what we call a Galois ring extension. So you need to take an irreducible polynomial of large enough degree and consider polynomials modulo that polynomial. For practical parameters, this degree is between 46 and 72, and none of the previous works have actually addressed the issue of how arithmetic will look over this ring, computationally speaking. In terms of communication, this check is very nice because it's independent of the number of multiplications you're checking. But in terms of computation, no one has explored the feasibility of this. We implemented, we use a library, a very optimized library for computation over this ring, and we see that it can produce only about 22,000 multiplications per second. Now, after considering how many multiplications in this ring are needed to check different secure multiplications for different protocols, we see that this leads to only 22 secure multiplications per second. This is an extremely low number, especially when we compare it to our protocol here that produces about 400,000 secure multiplications per second. This is a problem that has been ignored in previous works, and the conclusion is that unless computation over these ring extensions improve, this is simply not practical. Okay, so with this aside, I think I'm ready to describe to you how our 4-party protocol works. It's actually very simple. I can describe it in a few slides. So the main building block is the standard replicated secret sharing, in which if you want to secret share a value x between 4 parties, first you additively split this value into 4 terms, x1, x2, x3, x4, identified by colors. It will be useful in a moment. And then you assign the shares to the parties in the following ways. P1, color yellow, will get the shares corresponding to colors different to yellow. So blue, purple, and green. Or in terms of indexes, it gets the shares corresponding to an index different to 1. P2 gets shares of indexes different to 2, and similar for P3 and P4. So it's easy to see that one single party doesn't have enough information to know what the secret is. Now, this secret sharing scheme is additively homomorphic. So if the parties have shares of 2 values, they can locally add up their shares to get shares of the sum. It's easy to see that this holds. For multiplication, the process is more involved. So we can see that if x and y are additively split, as is in the whiteboard, then the product of x and y consists of all these cross terms. We have all different kinds of cross terms. We have some of them having only one color, so x1, y1 has only yellow, for example, and we have some of them having 2 colors at most, x1, y2 plus y1, x2, for instance. It has yellow and blue. So the plan is to design a method to obtain shares of each one of these cross terms. These shares are represented by brackets. So after the parties obtain shares of each one of these cross terms, the parties can locally add up those shares to obtain shares of x times y. So let's see, for example, how they can get shares of x1, y1. This one is actually very simple. We can split x1, y1 as these 4 terms. And then P2, P3, and P4, they already had x1, y1. So basically, they already have shares of x1, y1 as described in the whiteboard. And this requires no interaction at all. So for cross terms that only have one color, the parties can obtain shares non-interactively. Now, for cross terms that have two colors, the process is a bit more complex, because x1, y2, for example, the one we're considering here, x1, y2 plus y1, x2, is only known by two parties, not by three parties. It is known by P3 and P4. So to get a shares of these, we're going to proceed as follows. First, we're going to assume that they have a p-share keys. This is a one-time thing that can be used for a lot of multiplications. We assume that P2, P3, and P4, they have a shared key that we call K. And the way that we're going to additively split Z is as follows. Is as some random value R produced as a PRG of this random key K, plus Z minus R plus 0 plus 0. We see that, of course, all these add up to Z. Now, the replication that the parties will have is as explained at the bottom of the slide. And we can see that P2, P3, P4, they have R, so they can compute this value. They have Z minus R. The one that is missing is P1. P1 doesn't have Z minus R. To fix this is very simple. P3 will send Z minus R to P1, and P4 will send a hash of Z minus R, so that P1 can check that the two values are the same. At this point, there is some a chat between the parties to be able to identify who is the correct party. But the point of this is that after discussing these values don't match, these values match, they didn't send this value, and so on, the parties can completely identify a semi-corrupt pair. And this is basically the description of our multiplication protocol. So as a summary, we saw the multiplication protocol of our four-party computation protocol. It is suitable for computation over nice rings, tolerates one corruption, satisfies a stronger notion of private robustness, but has good complexity and has good concrete performance. It doesn't rely on expensive checks, and it doesn't hide anything behind a preprocessing phase. And with this, I would like to conclude my talk. Please feel free to ping me if you have any questions about our work. Thank you.